Okay. So once your data has been normalized or you've checked that it's normal, you can then put it into a program and get the analysis of variance table. And it's doing exactly what I've explained to you in the spreadsheet. So you had 20 cultivars, you had 3 reps. It works out the sum of squares, it works out the error. You got the total sum of squares. You divide that by the degrees of freedom, and it will give you an F ratio and a probability value here. Now, again, here you can see that the reps, or the blocks, it's probably better to refer to them as blocks, did not vary. So in fact, your field was fairly uniform after all. And you can see that I've got a high F ratio here and a high probability, and it tells me that my cultivars differ significantly. But what it doesn't tell you is which cultivars differ from what. Okay. So this then just becomes the beginning, and it tells you what your variation is, or what the different sources of variation are, and whether they are significant or not in relation to the error, which is chance variation that you didn't vary. Now from that table you can work out quite a few things. You can work out your coefficient of variation. We spoke about that the other day, which is your mean square error. Your mean square error is basically your variance divided by the mean, and of course you're going to square root to get your standard deviation, and it will tell you that your coefficient of variation is 7.5%. Now we discussed that the other day. I don't want to spend too much time on it, but the point is this experiment was pretty good. And of course it's very good because it's fictitious data. Okay. But I didn't say that. Okay. It's biased. Okay, but that's for demonstration purposes. And as we said the other day, it's an arbitrary value here. My arbitrary value is 20%. Pure statisticians will tell you 10%. And some people will even go higher, because very often, even though you have a high CV, the data are still good, or you can use other methods. You know, if it's multi-season data, you can look at rank correlations and things like that. We'll get to that in the next day or two. So, okay. Anyway, that's your coefficient of variation. What's more important is I want to know which cultivars differ from which cultivars. And we have various means tests that we can use to separate out the cultivar means. The one that's very often used is LSD, least significant differences. The agronomists like to use Tukey or student Newman-Keels. There are a couple of these that can be applied. Now basically the least significant difference is worked out by 2 mean squared error over the number of reps times the t-value that corresponds with your error degrees of freedom. So that you'd look up in a table. Okay, so 38 degrees of freedom, the t-value would be 2.021. So you would then work out your mean, your LSD, 2 times mean square error. It's supposed to be 29.19. Sorry, it's a misprint. I'll fix that up. Okay, divided by 3, and essentially you'd get a number like 7.23. Now what does that 7.23 tell me? If I take cultivars here and I list them from lowest to highest, remember I wanted to check susceptibility, I then look for differences greater than, what was the value? 7. 7. Okay, 7, close enough. Okay. So in other words, 16 and 7, okay, they overlap. So there is no significant difference between those cultivars. So for all intents and purposes, they come, those means don't differ, even though by looking at them, it looks pretty good. Okay. But they don't differ because of the variation that is still there in the trial and the data. That one there has a difference that's greater than 7 between those two. So therefore, I can say with a 95% probability, because I used that 95% probability t-value in my calculation, that that cultivar differs significantly from that cultivar in terms of disease severity, or whatever I was measuring. And so you can then group the cultivars according to the LSD. Yeah, you can see there's a group of cultivars that are very susceptible, and they're significantly different from all the others that are there. So immediately you can then make deductions about the cultivars and where they are in relation to one another. So if I'm making a recommendation for cultivars, okay, I'll probably obviously recommend that one as a first choice, but let's say that that's a higher yielding cultivar than that one. I'll go and tell the farmer, look, there's no significant difference between these two, rather plant the higher yielding cultivar than the lower yielding cultivar. Okay, so it then becomes a tool for recommendation or for making conclusions about the behavior of the cultivars. So the conclusion is that PAR 1234 is the most resistant but not significantly different from MFC 3354. No significance between that group of cultivars there. Okay, so you can then reach conclusions based on statistical analysis. In other words, you can be 95% sure that you are reaching the right conclusion.